Okay, I believe I've sorted everything. Let's make a start. Cool. So this class is going to dive further into the exponentials and logarithm stuff, specifically on how we solve and graph exponentials. So let's take a look. There's more or less three main kinds of things that can come up when it comes to solving exponentials. The most basic of which is to simply just equate exponents. So essentially, you have this kind of scenario when you have what are more simpler exponentials, where essentially what you're trying to do is rewrite both sides of the equation so that they have the same base. And by base, we're looking at having something to a power. That thing that is being raised to a power is the base, right? So 27 can be rewritten as 3 cubed. From here, you can see the similarity between these two things. You have same base of 3, power is x versus power of 3. You can, when there's the same base, you could now ignore the base and then go straight into saying that x is going to be 3. All right, if you imagine putting a 3 here, we're just saying that 3 cubed is equal to 3 cubed. Nothing too crazy. Can get a little bit more difficult, mainly when you have like an addition or subtraction between your powers. Fundamentally, it's still the same thing. You look at the 25 and the 5, you realize that 25 can be broken down into 5 squared, so you're getting it down to that same base. Using your index laws, you can then sort of combine those exponents, and because you now have same base, you can ignore those bases and just say power of the first is equal to power of the second, and then just go from there. Those powers, I guess, could be quite complicated. Like you could put all sorts of nonsense in there. The final step after equating those two things is going to be only as difficult as the powers. And as far as I've ever seen, they've pretty much always been linear. If not, maybe you'll get a quadratic in there. Any questions about that so far? Okay. What's typically a lot more complicated is when you start getting a decent amount more exponential terms in your equation. So in this case, I've got like a 3 to the power of 2x, 6 times 3 to the x. You got a constant in there, equals 0. That's when we use what's referred to as a quadratic solution. So essentially, we're going to try and rewrite, or at least try to observe the hidden quadratic that exists underneath. We'll talk about a couple of ways as far as identifying when you can use a quadratic solution and when not to. But for now, let's just assume that we can. First thing you want to do is make sure that everything has the same base in it, or at least the exponentials have the same base. That's going to be a very common thing to do. And in this case, they already have, right? 3 to the 2x, 3 to the x, they are the same base of 3. From there, converting to a quadratic form simply means that you want to figure out what the simplest, or it's not quite right to say lowest common factor, but like what is the simplest exponential that you can create from what we have. And that's going to be this 3 to the power of x here. All right. If you do some index law stuff by separating that 2 off of the x, you'll see that you have 2 copies of 3 to the power of x that you can work with. Now, all of this that we're doing here is simply just making it look easier. Technically, you don't need to do this. Technically, you don't need to substitute a equals 3 to the power of x, but it does make life look a lot easier because all of a sudden when you do that, that's just a quadratic. You could potentially see that here as well. You could see there's a 2x, a 1x, and an 0x. You can immediately think, oh, yep, that's quadratic, and then solve it like you would from a quadratic there, but this I find at least sort of clarifies your thinking a bit easier. It makes it look more like a thing you're already used to, rather than it looking more foreign than it otherwise would have to be. But yeah, all that to say, technically you can go straight from here and solve it, as long as you know that's what you're doing. But okay, how do we solve quadratics? Well, usually it's going to be factorization. If not, you've got some quadratic formula to work with. I've never had it where there's been no solutions entirely. But I definitely have had it where only one of the solutions is valid, like in this scenario here, where essentially all we're doing is noticing that we have our two solutions, a equals -9, a equals 3, but reminder that a is of course an exponential. So instead of putting a equals those things, you put the exponential as equal to both of those things. You have two possibilities to solve for. 3 to the x equals 3 is the only one that has a valid solution. And the reason why is because there is no possible x value that would ever make 3 to the x become a negative number. If you choose a positive x and a more positive x, you're just going to get a bigger positive number, 3 to the power of 3, 3 to the power of 4, etc. And if you choose 0, well, that's just going to get you to 1. 3 to the power of 0 makes 1. And lastly, if you chose a negative index, you're just getting closer and closer to 0. Like for instance, 3 to the power of -1 is 1 over 3. 3 to the power of -2 is 1 over 3 squared. So 1 over 9. You're getting closer to 0, never actually becoming negative. That's at least how I prefer to think about why that has no solutions. The other thing you could do is literally just graph it. Like the statement 3 to the x equals -9 just means where on my graph does the equation of 3 to the x ever equal -9. So if I draw that out on the handwritten section, you've got 3 to the x up here, you've got -9 down here. They're just not going to touch. That's the way you do that method. Is there any questions on the execution of the method? Easy. Now let's look at why you would know to use that particular method. So, first thing to look at, I kind of pointed out a bit earlier, which is when you have these descending coefficients of x. So you're looking at like a 2x, a 1x, a no x sort of situation. All right, that's pretty indicative of quadratics. You got that descending rate. Worth also pointing out, it doesn't necessarily need to be 2, 1, 0. It could, for instance, be something like, if I were to again draw on the handwritten section, you could potentially have 3 to the 4x, then, I don't know, 6 times 3 to the 2x, and then some other constant, right? You still have the same sort of ratio, which is they're going from 4 down to 2 down to 0. They have this uniform, I guess you'd call it linear, descent downwards. The way you would solve this one, by the way, assuming it is even solvable, is you would do a equals 3 to the 2x, because now you just have so you have a squared plus 6a minus 27, which might actually be exactly what we had last time, isn't it? A squared plus 6a minus, yeah, okay. So you're just essentially changing what you choose as your a. What's the simplest exponential? Or at least the largest common factor there. Because technically speaking, you could break these both down into 3 to the x, but that means you've got a quartic that you're working for or working with rather than a quadratic, which is still solvable, right? You can still solve a quartic, but suddenly you're looking into either some interesting factorization techniques or worst case scenario, you're doing like your remainder and factor theorem to simplify that down, which is a lot of effort. But okay, so that's the first kind of feature to look for, these linearly descending powers of x. If for whatever reason you can't identify that you have those, the next thing you could look for is just coefficients on the exponential terms. So we had like 6 times 3 to the x. This one's -2 times 3 to the x plus 2. Right, anytime you have a coefficient on there, it's pretty likely that doing a where is it? I don't quite have it. It's pretty likely that you can't use the equating exponents approach. Because even something as simple as just saying, sure, we have 3 to the x equals 27, but if we now have, and if I draw this out, if we now had 2 times 3 to the x equals 27, suddenly when we do our method, it's not going to quite work out, because now we're saying 2 times 3 cubed equals 3 cubed, which we obviously shouldn't do. So all that to say, when you have those coefficients, decently likely that equating exponents can break, and so you have to rely on another method. The other obvious one, of course, being that you have multiple exponentials in your equation, and so you should probably use a quadratic formula or similar to try and solve it. Any questions on how to identify when you would potentially use that? Easy. The last one is a logarithmic solution. We've covered logarithms in other classes, so you should all be at least somewhat familiar with how to use logarithms. If I do need to go into any more detail, feel free to let me know. Basically, you can pretty much always use a logarithmic solution when you can't do an equating exponents approach. So even something simple like 5e to the x equals 4, right? There's no way to get 4 down to a base of e unless you really play with it. It's always technically possible, but usually it's a lot more trouble than it's worth. And so when you have these kinds of exponentials, fundamentally you just want to get the exponential term on its own. So in this case, you're just dividing both sides by 5. And then once you have that, you just do the flip to log. I know when I was studying in school, figuring out the differences between where things go in the log can be quite difficult to remember. The thing that I like to consider is that the base of the exponential and the base of the log are literally called the same thing. And so that at least gives you at least one anchor point to work off of. If your base of exponential is e, then the base of the log should be e when you flip it. Then from there, you got to figure out, hey, do I put the 4/5 over here or do I put the x over here? The way I've always remembered which way to go is more so based in why I would even bother converting to log to begin with. If the x did go in the log, it would just make it more complicated to solve, not less complicated. Now, I know that's not like a mathematically sound explanation as to why x goes here, but it's at least what I think in my mind because, I don't know, it's just what I think when I'm doing them. And so that's what reminds me to put x on the equal sign rather than inside the brackets of the log. We're trying to simplify things, not make it more difficult. Whatever mental gymnastics you need to do to memorize which way the log goes is up to you. That's just what I've got personally going on in my head. If there's anything more complicated than just x inside that power, then you'll have to do a bit more rearranging here. That's what step 3 is all about, but this one's a fairly chill one. Like for instance, if this was 2x, then you'd have a 2x here. You would just divide both sides by 2 to get the x on its own. Any questions on that one? All right. Now, there's a couple of ways you can do exponential inequalities. The way I'm going to recommend is a method by which you choose your logarithm to be the same base as the exponential that you have. All right, let's have a look. So when you have inequalities like this, one of the challenges is that the inequality will likely flip when you try to solve it. When you have decimal type stuff like this, or pretty much any exponential inequality, the way to go about it is to wrap both sides of the equation with a logarithm. Technically, you're able to choose whatever base you want. That's what I'm going to detail here. My recommendation is choose the same base as the exponential. And the reason why is because when you do your simplification steps, you're going to get to this stage here where base and bracket are identical, and so they just cancel down immediately. No further things to consider. The con with having to do that is knowing that whenever you take a logarithm with a base between 0 and 1, you flip the direction of the inequality. So instead of it being less than or equal to, it's now greater than or equal to because we chose our base to be between 0 and 1. That's the downside of doing it that way. As for the actual arithmetic, fundamentally once you've put a logarithm around both sides of the equation, you use the power law to bring this x out and cancel that down. So you trade difficulty at the beginning for ease at the end. If you, however, decide, screw that, don't want to do it, instead I'm going to do whatever base I feel like. In this case, I'm choosing natural log, base e. You're still following the same sort of steps. You don't have to worry about your flip of the inequality, at least not yet. You do the power law to bring it out. Now, here's the thing. To get x on its own, you've got to divide by natural log of 0.4. Maybe you guys are more familiar with logs than me. I couldn't off the bat tell you if this is negative or positive. I can in this scenario because I've written these notes and done this lecture a couple of times, so I already know it's negative. But at a glance, that can be a bit challenging to figure out. So here's how you can try and figure out whether you're dividing by a negative or a positive. Sorry, I'll roll that back a bit. The reason why it even matters if this is negative or positive is because we have inequalities. When you multiply or divide by a negative, you need to flip the direction of the inequality. So with that said now, here's how you actually handle that. Take whatever the log is, let it equal to something. We don't know what it is. Let's say it's equal to y. From there, convert to an exponential. This makes it a lot easier to sort of track what y could potentially be, whether it's a positive or negative number. So you take that, you flip, and you start thinking, okay, well, if I chose any positive y value, I'm just going to get a number that's bigger than e. E is approximately 2.7, by the way. So any number bigger than 2.7, definitely bigger than 0.4. If I choose e to the 0, I'm going to get 1. Still not quite 0.4. It's only when we start choosing negative indexes that we're going to get closer and closer to 0. So for that reason, y must be negative, which means this log must be negative. So when you do this division, you now need to flip this sign later on. And the other disadvantage is that you now have 2 logs on one side versus just having 1 log. The CAS does this one, by the way. It just does this instead. So keep that in mind. If your CAS shows you something that you don't have, this statement is in fact the same thing as this statement. Logs can be a bit weird in that way. So it's really just up to you which one of those you'd rather do. They both have upsides and downsides. My preference is to do this because it teaches good habits around how to handle this base, right? Even just in the sketching of logs, when you have base between 0 and 1, you should flip. So I think that teaches better habits. But if, at the end of the day, we're just trying to make it easier for you, not harder. And so whichever one of these you want to do is up to your own preference. Any questions on either of those approaches? That's solving exponentials. Next up, graphing exponentials. So, basic graph of the exponential, I kind of showed you one from before. You're basically just going up and right at an exponential rate. It's going to have an asymptote. The reason why is, well, if you imagine testing certain x values, you'll notice that as the power increases linearly, the y values increase exponentially. So 1 to 2 to 3, you look at it, 2 to the power 1 is 2, 2 squared is 4, 2 cubed is 8. The y values are rapidly increasing. Whereas when you choose negatives, it's now rapidly decreasing, right? But getting closer to 0, because now that 2, 4, and 8 are in the denominator rather than the numerator, which is why you get this asymptote that approaches that side. It is worth highlighting that, by the way, like how you can analyze these graphs, because that'll help much more, not just for exponentials, but sometimes you'll get like weirder graphs, like one that came up literally last lesson for me was something like x sine x, right? Not something that's taught in methods, how to graph that. But like, if you know that x is this linear in the handwritten section, and sine x is this, then x times sine x would just mean you overlay them both and then multiply them together. So little tricks like being able to even test some values, right? Like if you sub in pi over 4, for instance, we know what sine of pi over 4 is. We can get an estimate of what the, or not even just an estimate, like an actual value for what the y would be at those spots. So little tricks like this can help with more complicated graphs that aren't necessarily tested in methods. But anyway, we're not quite doing that today. Back to the screen share. If the base is bigger, then the effect that we see is magnified, right? Because we're now looking at like 10 squared, 10 cubed, much bigger. And so it's going to rise much faster, but it's also going to fall much faster as well. The other thing to consider, like I mentioned before, is what happens if your base is between 0 and 1. That's when you start getting reflections that happen in your graph. So specifically, it ends up looking like a reflection in the y-axis, right? So a base of a half looks like the y-axis reflection of a base of 2. And you can again prove or at least observe what's going on by testing some x values. You can see we just get the opposite effect, where the positive x values are going closer to 0, but the negative x values are making bigger and bigger y values. Yeah, same thing here about bases. Dilation factor works similarly. The only nuance between them is that the dilation factor is a multiplier after any exponentiation, whereas when you change bases, they'll still cross over at the same sort of spot, at least as far as the y-axis is concerned. Whereas with dilation factors, because you're now, well, maybe I'll explain this a bit better. Y-axis means x equals 0, and anything power 0 is going to be 1, which is why they cross over at the same spot. Whereas when you slap a multiplier on that at the end, suddenly you're shifting that 1 upwards to 3 in this case, or a third in this case. These semantics only really matter when you're forced to actually explain it. If you're doing like an investigation and they say, what's the difference between the dilation factor and the base? These are things you might start bringing up. I know different schools will do different things around that. It's also just decent theory to have as far as knowing the underlying concept of what's actually going on with an exponential. But fundamentally, if you're just trying to sketch these by hand, your base basically doesn't matter unless it's between 0 and 1. And your dilation factor pretty much doesn't matter at all because you'll be doing the exact same shape. Same thing here. Dilate on the x variable. You're multiplying this, so it's going to shoot up faster. You're dividing this, so it's going to taper off, or at least shoot up slower, perhaps. Reflections, they work as they always have. So negative at the front means we're reflecting in the x. Just keep in mind that because the base is also a type of reflection term, you now have to consider 2 possibilities for reflections. So if you normally have base greater than 1, which normally you do, it'll end up looking like this blue line. Whereas if you have this scenario, it's going to look like this instead. Reflecting the y-axis gets kind of weird because now you could double up on it. So for instance, if your base is between 0 and 1, and then you flip in the y-axis, it's like as if you had just started with 2 to the power of x to begin with. So yeah, that's reflections. Translations, pretty much only the vertical translation matters. Horizontal translation will change where it cuts at the x-axis, well, at the y-axis rather. But again, as far as you sketching it by hand, you don't really care because you're going to label it something anyway. You're just going to change the number that you put on the tick. The vertical translation matters a great deal more because it's going to set where your vertical asymptote is now going to be located. So when you have a plus at the front, your y asymptote is now going to be whatever that plus is. If you have a minus, same deal. Yeah, those are the fundamentals around that. Any questions around that? Easy. So as far as what you have to actually care about when it comes to sketching by hand, first is horizontal asymptote. That's going to be whatever this plus c ends up being. X-intercept, you solve by y equals 0, like you would for basically any other graph. In the context of exponentials, however, it's often the case you'll have to do the logarithmic solution. That was this thing over here, where you get the exponential on its own, like we're doing here. All right, there's these factors that we're going to pull to the other side, flip to log, and then get the x bit on its own. So it's often the case you'll have to flip to a log to get your x-intercept, which is why in the Cambridge book, the first sketching of exponentials, maybe they only do one. Pretty sure they say don't do x-intercepts because they haven't actually taught logs before that point in the chapter. But since you've seen it, you can obviously have a go at it yourself. Y-intercept, a lot easier. Just sub in x equals 0, and sometimes it's literally just that easy. It just simplifies down, and then that's your answer. Can't be simplified any further. As far as how that looks, let's try an example. So, first things first, make sure you can identify all of the actual transformation factors that you care about. In this case, because there's a multiplier of 3 at the front here, one of the things you definitely want to get is distributing that through. This is more so good habits, taking this common factor of 2 at the front to reveal a horizontal translation of 3. We kind of already talked earlier that the horizontal translation doesn't even really matter for sketching by hand. This is more so just a good habit, being able to see, yep, translate 3, translate 1, dilate 3, dilate half, and negative. You know, being able to spot what all of your things are is good practice for all graphs, not just this one. Asymptotes, usually the easiest thing to find. That's going to be that plus 1. That's why we do this distribution. You're not going to say it's negative a third, you're going to say it's plus 1. You've got to make sure to factor everything through. Make sure you identify any reflection terms that come up. The only one that comes up here is this negative, which means it's now going to point down rather than up. Our base is e, which is roughly 2.7, which is why you've got normally up and right, now it's down and right. Then from here, some intercepts, y equals 0 for x-axis, so sub in y equals 0, subtract 1, divide negative 3, gets you a third. The exponential is now on its own, so we can convert to a logarithm. Again, base e means base a log is e. This is what we're trying to solve, so it goes on the equal sign, and then a third goes in the brackets. And then from here, you know, divide by 2 plus 3, and that's going to get you your x-intercept, which you would label with that full thing, not the decimal, unless otherwise specified. So you will have these pretty long labels for things. And then, yeah, as I said before, this is usually pretty chill. X equals 0, like that's all you do. There's no simplification after that, unless you want to make this like not a fraction, or make it into a fraction rather, by removing the negative index. But this is probably neater because it's all in one nice line rather than taking up even more space on the axis. If you have endpoints, obviously sub those in. That's more so with like restricted domains. Yeah, that's about it. Any questions about how that one came together? Cool. There is probably only one more thing I'll talk about, which is, you know, you got these numbers here. How do I know that my graph is both positives or maybe it's both negatives? Like, how do I determine which one? Like, for instance, if I try and draw another thing on the handwritten bit, I could still have the same looking shape, but have it drop down like this instead. How do I know that I don't have those values here? Because it's kind of hard to figure out if what you have is a positive or a negative value, especially when you've got a negative on the e, right? And we saw before, natural log being a third, or having a fraction in the bracket made things a bit weird. Easiest way to go about that, if you look back at the pre-written screen share, is probably looking at the exponential term. That's the easiest one to start looking at. So in order of how you would start addressing this, you'd probably start by looking at the e term itself, right? So you've got this e to the power of -6. Well, negative indexes just means fractions. So realistically, we were saying this is -3 over e to the power of 6. Now, worth pointing out, e is approximately 2.7. You should know at least roughly what e is going to be. Even if you just say pi is e is 3, like the math meme that goes around, that's also fine, right? You don't need to be that granular with it. So, 1 over e to the 6 is going to be a pretty big denominator. So when you multiply that by -3, it just means that suddenly you have a very small negative number. So when you add 1 to that, it's still going to be a slightly positive result. Now, the good news is once you know that this is positive, there's only one way to draw your graph. Because if we go back to the handwritten bit, and we say, okay, cool, we know we've got a positive y-intercept, and we know we've got an asymptote at 1, or whatever it was, there's only really one way you can draw that, and that's to also go through the positive on the x-intercept as well. You can go backwards, but then you're drawing a completely different graph. And you have to go out of your way to make that happen. So if you just follow the natural curve of what it should look like, the other value will fall into place. You don't have to know what that value actually is. That's about it, really. So, is there any further questions as to basically anything I've discussed there? In the meantime, I'll pull up the the document that tells you the prescribed questions, and we'll create some breakout rooms unless anyone has any further questions they want to have a look at now. I believe that's made it through. Let's get into it. So again, you can download the book from there if you still somehow don't have a copy.
Okay.
Yo, what's up?
Is it possible you could just send a screenshot of the questions in the chat instead of a file?
Instead of a full Word doc? Yeah, okay. I'll see how... Yeah, this won't be too bad, actually. It's only a one-pager. Sometimes
Yeah.
it's a two-pager, but
Thank you.
yeah, no worries. All right, how did that come out? Readable?
Oh yeah, that's good. Thank you.
Sweet. Yeah, all right. Let's do it. Breakout rooms. Let's see. Like manually. Yeah, I'll just spam a few. That, and that, and that, and that. All right, cool. I'll do the rounds. How you going, Peter? Having tech trouble? Oh, I briefly heard that.
Yeah, I'm good. How are you?
Oh, good. Okay, yeah. I just set the breakout room stuck. I was wondering if you had tech issues.
Yeah, I'm trying to join it. It's not letting me.
Not letting you. Okay. Maybe I can send it again. To did something come up for that?
Yeah, let me click on it.
Yeah. Sweet. Um, Hey, hey, how you going?
Well, good, thanks.
Nice. So the private class is doing well for you?
Yeah, I mean, the first one that we did was pretty basic. It was just approximating area under the curve, but I
Mhm.
guess it's a good way to start. Um,
Yeah. Like you
so
you have control over that, by the way. What you want to have a look at, you can text ahead of time and be like, hey, let's have a look at this sort of stuff.
yeah, I mean, that's like I said, like let's just go from the start, and that was fair
Oh,
enough.
yeah, okay.
Yeah.
Sure. That is definitely the start.
Yeah.
Fair enough. Yeah. Is there anything you want me to have a look at?
Um, Let me have a look at the book real quick. So you guys did rates of change on Friday, right?
Yes. Yeah, we had a look at rates of change.
And was that just like the AROC and IROC, like the
Hmm.
average
Yeah.
and instantaneous?
So there was that, and it was like a brief touch on the kinematics stuff. So differences between displacement, velocity, acceleration. Very
Um,
brief.
yeah, I mean, I'm doing that in like what's called physics right now.
Ah, yeah, yeah, nice. Yeah, I
Yeah,
didn't realize how they actually put derivatives in the physics stuff recently. That wasn't there when I did physics in 2018.
yeah, I don't know how they do that, like, because
Yeah,
that's kind of more of a math sort of thing.
it is, isn't it? Yeah, it's very strange that it made it in there, but I guess I got well, not necessarily lucky because I had methods anyway, so it wasn't going to be bad if it was for me. Um, but yeah, no, works in your favor, so isn't that cool?
Yeah, well, I mean, there's not too much I want to look at because I know
Mhm.
chapters 2 to 7 pretty decently, I would
Nice.
say. And I mean, 9 to 11 could do some work, I guess, in terms of probability.
Hmm.
And I know I'm pretty good at circular, and then yeah, well, obviously we're doing this at the moment, so
Sure.
I'll
Yeah, yeah.
be I'll do this.
Cool. All right. Yeah, I mean, if you think about anything, of course, happy to address them. But if there's nothing in immediate you want me to have a look at, I'll do a few rounds. What do you think?
Yeah, no worries. That's fine.
Easy.
Cool.
Hello. Shock. Awake.
Hello.
How
Okay,
are you
so
doing, Charlotte?
I lost you for a second because I've got like a bunch of tabs open. I'm just trying to swipe through my laptop. Forgot where you were. But yes, hello.
Is there anything in particular you'd like me to have a look at?
I'm kind of just exploring 13C right now. I'm playing around with my CAS. Everything
Hmm.
is understandable at the moment, so I'll
That's good.
just tell you if I need some more assistance. I'm just kind of, yeah, it's kind of easy right now. So
Sure.
if I struggle, yeah, watch the next lesson be about this. So,
No worries. All right, I'll leave it to it then.
okay.
Hello. How you doing? Anything in particular you'd like me to have a look at?
No, nothing really right now.
Easy. Super easy then. No one's looking for anything in particular. It's awesome. Free. I guess I'll be chilling in the main room and maybe like raise a hand or something like that if there's anything you'd want me to have a look at.
Okay, thank you.
Easy.